Hello, my name is Bruce Crayenhoff, and this is my second screencast in this series on quantum computing. This all started with I had an interview at a quantum computing company. It piqued my interest, and so I'm learning enough to satisfy my interest, basically. Quantum computers are wild. We'll go over bits and pieces of this in the screencasts. And so this is not like your only resource to learn about quantum computing. It's a supplement to other resources, which I'll be linking to from my blog and from here. So this screencast, and it assumes a similar background to what I had. I've done some quantum mechanics, very rusty. So this screencast introduces the quantum gate computing programming model. And it gives some practice working with basic quantum gates, which I struggled with for a while when I was studying. So this will hopefully give you some fluency before we go on and use them in different algorithms. And so this is based on this paper. Anyways, this is a paper introducing, it's an introduction to various quantum computing algorithms and to the quantum computing programming model. So we're basically going to be going over this part of this paper here, and then we'll be doing some extra exercises on quantum gates. All right, and as usual, for the fraction 1 over square root of 2, I just use f to make things easier. Okay, so basic notation and definitions. So ket notation, this means that basis state, this means this one. A qubit is just, it's like a single spin, right? And so a single spin can be a certain fraction in spin, I don't know if that, I guess that'd be a certain fraction in spin up, a certain fraction in spin down, right? Alpha squared in spin up, beta squared in spin down, and they have phases, right? Alpha and beta have phases. And it's normalized, so the total probability is 1. So a unitary transformation is, so it's a matrix transformation where if you multiply it by its, I think it's Hermitian, let me see. Anyways, it's conjugate transpose. So you take the conjugate and you take the complex conjugate and you take the transpose of the matrix. You multiply those two together and you get I. So qubits, which are each a single spin, change state via a series of unitary transformations in a quantum computer. So these transforms will preserve the probability sum to 1 because I guess you've got, so after one of these transformations, our original state u will become u times s, right? Because it's transformed. And the total probability before will just be s dot product with s, right? So the total probability after, well, we do the same thing, but with these with the new vectors, right? And doing the dot product is the same, sorry, hold on. Sorry, this is not the dot product because we need to take the complex conjugate of this. I'm not sure how to do this symbol here. It looks kind of like a T. So you do the complex conjugate and the transpose there, and then you just multiply those. So similarly, we'll do the complex conjugate and the transpose. So we have that. which will just be that. And then this is a complex conjugate transpose, so these end up being I, right? There you go. So the total probability just stays the same, so it stays normalized to 1. So that's why we're using unitary transformations in quantum computing. Cool. So the tensor product of vector spaces, it's basically, we do every combination of everything. So you can see that alpha 1 comes from this gamma 1. And so you see that in this term, and you'll see that, yeah, in this term, and this term, and in this term, but these all have beta 1, right? Because they've got 1s in the first place. So yeah, so if we had the tensor product of 4 spin half particles, then we'd have 16 basis vectors, right? So these are kind of all the possible states of the system. And that's what we're actually going to be working on. So this is part of why quantum computers could do, they can solve certain problems way more effectively, because effectively you're working, when you do operations here, you can work on 8 states at once. Or once you have 10 qubits, you can work on 2 to the 10 states all at once. So a single calculation can kind of underneath be doing 2 to the 10, which is about 1,000 different calculations in parallel underneath. The only thing is at the end you've got the result all in terms of mixed states, and so you somehow have to separate or extract what you're interested in. Alright, so a gate is really just it's just a unitary transform that's actually implemented on your hardware, or sometimes they're implemented as software and they can be compiled to the ones that are on the hardware. So a unitary transformation is reversible because this times this equals I. Obviously the inverse of U is U complex conjugate transpose. So everything we do on a quantum computer is going to be reversible until we make a measurement. The universal gate set. This is a set of gates that can perform all possible quantum computations. And we'll be going over the gates later, but one example is there's this T gate, there's an H or Hadamard gate, and there's a C0 controlled NOT gate. These 3 gates together are a universal gate set, because together they can do everything we want, as long as we combine enough of them. So, how a quantum algorithm works is generally you've got some data to start with, right? Some classical data. You encode this data into qubits. Okay, so you initialize some qubits to be in certain states. Then you perform a sequence of gates, a sequence of these unitary transformations to the qubits. And then we measure some qubits at the end and we interpret the result classically. And that's all we do. And we just need to figure out how to combine the gates and initialize to get the results we want. All right, so next we're going to go over a few gates and what they do. So a very important gate in quantum computing seems to be the Hadamard, from what I've seen, or H gate. And it looks like this. Now if you take this and you apply it to Z eigenstates, you get the corresponding X eigenstates. So if you apply this to this, you'll see that it picks out this column, and so this is actually the X eigenstate, the X spin-up eigenstate. And apply it to this and you get the X spin-down eigenstate. Now H applied to the eigenstates of X give the corresponding eigenstates of Z back. So you can test this out. Now, if we take an eigenstate of z and we go to an eigenstate of x, and then we do another Hadamard and we go back there, that must mean that h times h is the identity, right? Because we end up back where we started. And you can check that fairly trivially. Multiply this by itself, and you will get the identity. So, pause the video and verify that for yourself. Cool. So the reason why this will be important is in terms of the z direction. Here, this is kind of half spin up and half spin down. So often we'll want to change things to be half spin up, half spin down, so that we get to do our calculations on kind of all the different possibilities. Just like looking up here, we have an even mix of all the different states here in terms of z. And then we'll do some calculations, and then we try and extract what we want from it. All right, this controlled NOT gate. This is Hadamard. I could be spelling it wrong. Controlled NOT gate. So it looks like this. So the first two here, the top part looks like an identities, and so that's if we have a 0 in the first place. So here these states don't change. If we apply the C0 though when there's a 1 in the first spot, which corresponds to these parts of this matrix, then, well, we're switching those two states. So 1, 0 becomes 1, 1, right? This second qubit here is being switched in those states. Yeah, and similarly this becomes that, right? Cool. And then there's the T gate, which looks like this. It's a phase shift. And so remember these three together, they're a universal gate set. We won't actually be seeing T that often in our algorithm, but if you take T to the power of 4, you're actually going to get one of these basic Pauli matrices. You're going to get sigma z if you take T to the power of 4. And so we'll actually be seeing sigma z more often, which could be implemented by 4 T gates. All right, and so, there's lots of possible gates, right? You'll see, but all of them we can implement using those three. This is like an AND gate. It's if two of the qubits are 1, then you can switch a third qubit. So it's basically an AND gate. Yeah, so anyways, there's lots of them. We won't go over these in detail. Cool, so first of all, we're going to practice applying some single qubit gates. So that would be the Hadamard and the T gate, except we're not going to work with a T gate. Basically, we're just going to work with the Hadamard and maybe some spins. And then we'll practice applying 2 qubit gates. In fact, I think we're only going to work with the controlled NOT. So let's dive in. So, maybe let's keep this handy here. All right, so Hadamard applied to state 0. What's this going to be? Well, applied to state 0, you'll just pick out the first column, and so you get it's evenly spread out between those two with a normalizing factor. Hadamard applied to state 1. So this is where you should stop the screencast, figure it out for yourself, and then I'll check the answer for each of these and skip, if it makes easy sense, just skip forward to the next one. Otherwise, my explanations might be helpful. So it picks out the second column, so so in both of these cases, we're getting the probability is evenly split between these two, right? It's just the phase here is different by pi or by a negative sign, right? So that's important to keep in mind. Like there's probability and there's phase. The probability is the same when you apply a Hadamard to both of these, but the phase is different. So what is a Hadamard applied to a state? What does it do to the state? Pause the video, figure it out. Well, 2 Hadamards gives you the identity, so this will just give you back your original state, right? Review of the Hadamards so far. All right, so say we have, this is an even mix of the states, positive phase or negative phase. What does a Hadamard apply to each of these do? Pause the video, figure it out. So there's an additional hint here, in case you're having troubles, which is to use the previous 3 answers. So let's just solve it here. So when we apply it to this, that's ultimately it's this, and we know 2 Hadamards then will take us back here, right? So a second Hadamard will bring us back to the 0 state. Similarly, this is the same as this, right? Different ways of writing it. So we're going to get back to state 1. Cool. Now, if we apply spin z to this state, what do we get? If we apply spin z to that state, what do we get? If we apply it to this and this, what do we get? And it might be helpful to remember that. So pause the video and figure it out. And here are the answers. I figure they're fairly self-explanatory. So if we take the Pauli spin X matrix and apply it to each of these, what do we get? And your hint is here. And there are the answers. All right, so now we've kind of covered a bunch of basics, and we're going to use this to figure out some stuff. So suppose that we know either we're in this state or in this state, right? But we're not sure which one of these, so we want to tell the difference between these. How could we figure this out? So pause the screencast, try and figure it out. So the issue here is the probability of being spin up or spin down is equal for both of these, right? So if we just measure, is it spin up? 50% of the time this will be spin up, 50% of this will be this one will be spin up. Same with spin down. So we can't just measure the z spin to get the answer. So what we want to do is we want to do a transformation to take advantage of the phase shift. Now, remember the Hadamard applied to that gives you this. So another Hadamard, which is this. So another Hadamard applied to this would give us a spin, like give us a 1, which is 0 spin up, so that would be spin down. Yeah, but anyways, it'll give us the 1 state back. Okay, so this will give us a 1 state, and this will give us a 0 state if we apply Hadamards to it, because really what we're looking at are this and this. So that's all we need to do. We need to apply a Hadamard, which changes this to that and this to that. Now we can measure it, and we can tell whether it was initially this or this by whether it is spin up or spin down after the Hadamard. Yeah, there you go. All right, so a tougher one here. Suppose our quantum computer has a Hadamard gate and it has a Pauli Z spin matrix available, but it doesn't have a gate, the Pauli X matrix. So what we want to do is we want to effectively create this gate using these. So try and figure out how to do that. So here's the answer. Hadamard, sigma z, Hadamard, you could figure it out. So there's kind of 2 ways that I can think of to figure this out. So first of all, we know 2 Hadamards gives you the identity, right? So we can first do a Hadamard. Right, okay. So Hadamards give us these states, and we know 2 Hadamards bring us back to where we came from. So the idea is, let's apply a Hadamard. We end up in one of these states. And then we're going to switch the sign of this one state with a sigma z. Right? So this goes to this, and this goes to that. Those 2 switch. So then when we apply the second Hadamard, they go back to the opposite z state to what they came from. Cool. And that's ultimately, yeah, remember that's the sigma x looks like that, right? Maybe I should copy this hint down. Cool. All right, so that's one way. Another way is to say, I know that the Hadamard maps between corresponding eigenstates of x, / z directions. So, okay, I want to do stuff with x eigenstates. So first of all, I'll map them to z eigenstates. Then I'll do the flip in the z direction, and then I'll map them back to the x eigenstates. Yeah, so that's what hopefully this makes sense. That's what I was just talking about. Cool. And so we are done the single gate exercises that I made. If your head's kind of spinning, it might be good to go over those again, or you probably want to go over them again either later or now. I found them a bit mind-bending for a while, so they can take some practice to get used to. All right, so we're going to apply some 2-qubit gates mixed with a few single qubit gates to get some stuff done. Now when we have a 2-qubit gate, we need to specify which 2 qubits it's acting on. And there's, like with a controlled NOT, there's the control gate, which here would be the gate 3, and then there's the gate that's being acted on, which here is the gate 1. So this is how I denote a controlled NOT applied to qubit 1, where qubit 3 is the control. Cool. Okay, so we're going to use the controlled NOT here, which remember is this, which does this to these 2 qubit states. So let's just store the z value of 1 qubit in another one. Figure out how to do that. So still, pause the video and try and do each of these yourself before you look at my answer. So what we can do, if we just care about the z value, we can initialize a second qubit in state 0 and then just do a controlled NOT. So in this case, we flip the second qubit and it ends up being 1, and so they end up being the same. Pretty simple. Cool. So detecting if exactly 1 qubit is spin up. So, hold on. Right. Yeah, so here we're just doing 2 C-naughts where we flip gate 3. And so if we flip it twice, there must have been 2, yeah, so if exactly one of them is in state 1, then we'll only flip state 3 once, and it'll end up being a 1. And so, yeah, so here I'm showing if we're in this initial state, after the first C-naught we end up in that one, after the second one we end up in that one, right? And so because we've got 2 1s, the third qubit ends up in state 0. So at the end we just measure the third qubit. So here's a mixed state. So only 1 out of the 2 initial qubits is in state 1. So it flips the first time, and then the second time it doesn't flip because here the control state is qubit 2, so we don't flip it. And okay, so this shows that exactly one of them was in a spin-up state. And similarly here, we only flip it once, it ends up being a 1. Here, in this state, we do no flips, and so it stays like that. Cool. So, yeah, so let's apply a double Hadamard, okay, to, yeah. So initially, you're in one of these 4 states, and let's see what happens when you apply a double Hadamard, which basically this just means that we apply a Hadamard to the first qubit and to the second qubit separately, okay? So this is the tensor product, and so you could think about these in terms of matrices, but the easiest way is just to think of, okay, the first Hadamard acts on the first state, the second Hadamard acts on the second qubit, and you get your result. So you could figure this out by, just applying the first Hadamard, see what you get, then apply the second Hadamard, which is good if you need to. Ultimately, the goal here is that you want to be able to figure this out kind of in one step in your head. So that what I'm trying to get you to do is some bigger chunking here, which will help you later on when you want to see, okay, how do I get there? If you can say, what if you can take bigger steps, it's easier to see the path to get where you want to get to, right? Cool. And so the answer is, well, on state 0, the Hadamard gives you positive of each of them. We get 2 1/√2, so we get a 1/2 ultimately. So it's just evenly spread out between all the possible states. If we have 0, 1, when the second qubit stays 1, that's where we get a negative. So we can see here the second qubit stayed 1, here it stayed 1, so that's where we got the negatives. Similarly here, where the first qubit stayed 1, that's where you get the negatives. Here, where either of them stay 1, you get a negative. So if both stay 1, you get a positive, because you get 2 negatives, and you get that state. Cool. So it will be valuable, as I said, to be able to go from here to here. Just like write this out directly from this in your head. Cool. Now this is, I'd say, a challenging problem to create a C0 from the reverse C0. So you could give this a try. I'm guessing that you'll need a bit of help. And so I have a hint here, which is, so first of all, what we're going to do is we're going to consider what happens when we apply the double Hadamard. Well, we get this, right? Now, ultimately, these are the states we want to end up in, right? Ultimately, the first qubit is a control on the second one. So these two should switch. Hold on. Sorry. So, okay. No, we're using these to get this effect. Yeah. So 2 is the control, 1 is the one that's being flipped. Okay. So these two states should be flipped, because that's where the second one is a 1. And so, yeah, this becomes this, and that. Okay, cool. So those two have flipped. So this is ultimately what we want to get to. And so the trick we're going to use is, we know Hadamards, we can do a Hadamard to get these. If you do another Hadamard on these, we would end up back here, right? So what we're going to thinking is we do a Hadamard to get here, and then we want to do some stuff to basically, we want to switch this with this, and then we know another Hadamard will take us back here. All right, so the Hadamards of these are this, and if we compare this column here to this column here, the differences are really, some negative and positive signs here. All right. So we want to switch some negative and positive signs here. So we could use, sigma Z type gate, except a sigma Z gate okay, if we applied it on the first qubit, we could switch the signs of both of these. That would work. Hold on, but then, yeah, no, it wouldn't change the sign of the 0. I think a sigma Z gate might work as well. But another thing we can do is we can do the C0 1 2. So 1 is the control. So okay, so it'll always switch the 2 in the last column here, right? Because that's where the first qubit is a 1, right? So it'll switch this to 1 1, and then it'll switch this to 1 0, which, this becomes 1 1, that becomes 1 0, and really there's no change. It'll change this to 1 1 and this to 1 0, which means the 1 0 will now have a negative sign, right? And the 1, 1, because it came from this, will now have a positive sign, right? Okay, so the C0, 1, 2 would do the change here that we need. Here it would make no difference because these are both negative, so if you switch them, the phase stays the same. And if we apply it to this, again, because there's only a single negative here, it would give us the change in negative signs. Cool. So that's exactly what we need. So we're going to do the double Hadamard. Then we do apply C0, 1, 2, which switches those signs. And so now we recognize that if we apply a double Hadamard again, we're just going to get back to these, right? Because, yeah, essentially this is now the same as that. And this is the same as that. Yeah, cool. Now this is this intuitive for you? Probably not. Because what we had is we used Hadamards. So these act on each gate individually, right? And then we use a controlled NOT. So this is, 1 isn't changing here. This is just changing Qubit 2, right? Changing Qubit 2 based on the value of 1. And then we do some other Hadamards, and what has changed? It's actually the first qubit has somehow changed here, which is pretty crazy. So yeah, and I'd say pretty counterintuitive, and it has to do with, the only difference between the Hadamards of this and this is, well, it's just some phases of some of the states, right? And we can, by acting on the second qubit, we can change some phases by switching those, which after we do the reverse Hadamards, that ends up changing the first qubit, which, regular computers don't do this, right? This is called the phase kickback trick, I believe, and is pretty wild, I find. All right, so that concludes the quantum gate practice. So maybe do those again today. I would definitely do them again tomorrow to go through these problems, just to get the fluency. So like the rest of the screencasts will make more sense as you hopefully cover them over time and do associated reading as well. All right, advantages of quantum computers over classical. Well, there's superposition, which is, we talked about, like, after the Hadamard, this is in all of these states at once, right? A quarter of a probability of being in all of the states, basically. And so you can do calculations on exponentially many states at once. And there's entanglement, which is that spins can be totally perfectly correlated. So if you measure this spin, and then later you measure some other spin, you can get that they'll always be the same, for example. If that's one way to entangle them. And there's other ways, but you can make them like, so the knowing one spin gives you perfect information about the other spin. Cool. Now, when we get to real quantum computers, they only implement some gates, right? So, there's going to be physical locations of each different qubit, and so you're not going to be able to create gates between arbitrary qubits easily, at least in terms of hardware. So they have a limited set of implemented gates, but they might have a larger instruction set, so they can allow you to, you can use any of this larger class of gates, and then we know how to, if you use this gate, we can actually convert it into one of the ones on the hardware, right? And if you want to use that gate, well, that converts into these 3 gates on the hardware, right? Now, if we want to optimize our algorithm and reduce error, we probably want to use fewer gates. It'll make it quicker, and these quantum computers aren't perfect, so there's some error the more gates you use. So to reduce error, we might want to actually pay attention to the underlying actually implemented gates so that we use fewer gates overall. And in particular, the 2 qubit gates tend to be limited because you can't. Not all of the qubits are connected. And yeah, so there's known ways, like we just went over one. If we have a C0, 1, 2, we can use that to implement a C0, 2, 1, right? So there's known ways to combine the gates we have to get the gates that we want, right? And as I was mentioning, I mean, there's some noise. The gates aren't perfect. And quantumness, so that's like, where spins are totally correlated and whatnot. This is gradually lost over time, apparently. And so this limits the depth of your algorithm, because you need to be able to quickly get through all your instruction set before these effects become too significant. All right. So lastly, remember this is a complement to some reading. So here is your recommended homework, which is to read Lecture 1 of The Overview of Quantum Information by John Watrous. All right, I found the link. So just follow this link, and so you can open up the first and second lectures here, the overview and the rest of the overview. And also I would go over the quantum gates problems again. I'd definitely go over them tomorrow to review them after some sleep, and maybe today as well. Maybe again, maybe even a third time, I'm not sure. You judge your fluency in these things. And then come back for the next screencast. Thanks for watching.